So in this video, let us discuss about the time period of oscillation of a mass which is attached to the end of a spring having a mass. So let's consider a spring. At the end of the spring, there is a mass attached, let's say small letter m. And we have considered the mass of the spring. Let the mass of the spring be m. Now let the length of the spring, let's take that as L, and let us consider a small section of the spring in here. Let this be the small section of the spring of thickness, let's say some dx, and let the distance of this section from the left end be x. You can call this point as O. Let this point be A. This point be A. Now let this small mass is the small mass of this small section be some dm. Okay. First we need to find the kinetic energy of the spring. That is, let dk means k represents the kinetic energy. D stands for the small value of kinetic energy. dk be the kinetic energy of the mass dm. Okay. Now we know the expression for kinetic energy is equal to half mv square. Here m is the small mass dm. Let's take the velocity of this mass be some v dash. So we can write half into mass into velocity square, v dash square. Let's call that as equation number 1. We know the kinetic energy is equal to half mass into velocity square. Clear? Now let's take the velocity of this mass be v at any instant. Now we need to write this mass in terms of the mass of the spring. We have the linear density. Linear density means the mass per unit length. We consider this spring as is having a uniform linear mass density or simply linear density. So the mass per unit length of this spring is same everywhere. So you can write the mass of the spring by its length is equal to mass of this small section by its length. Since at every point mass per unit length is same, so you can write dm is equal to m divided by L into dx. Call that as equation number 2. Now we know the velocity at any section of this spring is directly proportional to velocity at which the mass oscillates. Or you can say v dash is related to v, and you can write v dash is equal to x divided by L into v. You can verify this, that is when x is equal to 0, that is this will be 0, you can say v dash equal to 0. That is at the point O, x is equal to 0 means at the point O there is no velocity for the fixed end, that is at the left end. And when x is equal to L, that is at the extreme right end, you can say v dash is equal to this x becomes L, so L by L times v, which implies v dash is equal to v. That is true. That is true also, because at the right end, both the end of the spring and the mass is having the same velocity, v. Clear? So we can write v dash is equal to x by L v. But in reality, there is some error associated with this equation, because you cannot say the velocity at a section of the spring linearly depends on the oscillation velocity of the oscillation of the end mass, because when we take the extreme values as we got here, it is true, but when you take the value at the middle, this x becomes L by 2, then v dash is equal to x, this is equal to L by 2 by L times v, which means v dash equal to v by 2. So you cannot say that velocity at the midpoint is half the velocity of the mass. So there is some kind of error associated with this equation, but in every others and in every consideration, they took the velocity like this. So, but when the spring is very small, this error can be neglected. But when the spring is very large, that is the length of the spring is too much, we'll get a greater error. Clear? So we can substitute all the values in here. So dk is equal to half dm, you can write it as m upon L dx into v dash square is equal to x divided by L v whole square. Clear? Simplifying, you will get dk is equal to half m by L dx into x square by L square v square. So rearranging, let me erase this. Rearranging, you will get dk is equal to, you can take this v square L square to the left, so it will be half m by L into v square by L square into x square dx. So this will give dk is equal to m v square divided by 2L cube x square dx. So in order to get the total kinetic energy, you have to integrate. Let's K represents the total kinetic energy. This is the kinetic energy of the spring. Okay. You have to integrate. See, the variable in here is x. So x varies from here. X is equal to 0 at O, and here x is equal to L. So x varies from 0 to x is equal to L. This dk. You can write 0 to L m v square by 2L cube x square dx. And all these values, that is mv square by 2L cube, are all constants. So you can take that out. So this will become mv square by 2L cube integral 0 to L x square dx. This is equal to mv square divided by 2L cube. Integral of x square is x cube divided by 3. Now you have to put the lower and upper limit. So 0 to L. So simplifying this, you will get mv square divided by 2L cube into, first put the upper limit, so L cube by 3 minus then the lower limit, 0 cube by 3. No need to put the lower limit since the value of x is 0. So kinetic energy becomes mv square by 2L cube into L cube by 3. You can cancel this L cube. So the kinetic energy is equal to mv square divided by 6. Clear? So the kinetic energy, you can write it like this. Kinetic energy is equal to 1 by 6 mv square. Call that as equation number 3. Now we know the kinetic energy of the, let me erase this. You know the kinetic energy of the whole system. Kinetic energy of the system. Let's take kinetic energy total is equal to, we have, it is equal to kinetic energy of the spring plus kinetic energy of the mass at the end. But we know the kinetic energy of the spring is equal to K, which is equal to half 1 by 6 mv square, plus kinetic energy of the mass is equal to half mass mv square. Clear? Since the kinetic energy of this mass is actually half mv square, since it is oscillating with the velocity v. So this can be written as 1 by 6 mv square plus this will become, you can multiply both the numerator and denominator with 3. So mv square divided by 6, multiplying both the numerator and denominator with 3. Now you can take that 1 by 6 out. So 1 by 6 into m plus 3m into v square. Now this can be written as 1 by 2 into 1 by 3. See, 1 by 6 equal to 1 by 2 into 1 by 3 times m plus 3m times v square. And if you take the 1 by 3 into the brackets, you will get total kinetic energy is equal to 1 by 2. This is equal to m by 3 plus 3m divided by 3. I just took the 1 by 3 to the brackets, v square. So you will get the expression as the total kinetic energy is equal to half m by 3 plus m, 3m by 3 is m, into v square. So this is the total kinetic energy. Now you just take the whole the mass, this system as a single unit, and we can write the total kinetic energy is equal to half m, the mass of the system, or you can write effective mass times v square. Call this as equation number 4. This as equation number, let's say, 5. When you compare 4 and 5, you will get 1 by 2 m effective v square is equal to 1 by 2 m by 3 plus m into v square. Cancel this half and v square. So the effective mass is equal to m by 3 plus m. Clear? So this is the expression for the effective mass. And from this relation itself, you can find that the effective mass of the spring, that is effective mass of the spring, is actually m by 3. Clear? This is the expression for the effective mass of the spring. So even though the mass of the spring is m, its effective value only comes to m by 3. Clear? Now we know the expression for the time period t is equal to 2 pi root of effective mass of the system divided by k, the spring constant. So we have the time period t is equal to 2 pi Root of effective mass here is m by 3 plus m divided by k. So this is the expression for the time period of oscillation of a mass which is attached to a spring having mass capital M. Clear?